Today we are going to explore how enhanced bit resolution differs from low-pass filtering and Picoscope. For that, I created a waveform that resembles a compression test waveform, but I do have two versions, one without the noise and one that is noisy. I took that waveform and fed it into arbitrary wave generator over Picoscope that was sampling at 1 megasample per second on 2 channels. Then I saved that waveform. Now we are going to open the resulting file and see what happens when we apply enhanced bit resolution and low-pass filtering. I have started the Picoscope in demo mode, and we are ready to open the waveform. So as you can see, we have a lot of those waveforms repeated, but I zoomed in 2 of them, just like we had in the octave plot. We have one that is without the noise and one that has noise in it. The waveforms are currently identical on both channels, but let's go ahead and apply enhanced bit resolution to channel A. If we do that, we get much less noisy waveform on the left, and the waveform that had no noise is almost unchanged. Though there are some differences. We will see them when we set the offset of the channel A back to 0 and merge the graphs. So we see that here, where we have a step function, there is a little bit of a difference. Let's zoom on it. Where we see a step function in the true waveform, we see a piecewise linear function in channel A with a non-vertical slope. Also note that it begins earlier than the true waveform. How much earlier? Let's get the cursors in and see what they tell us. So it takes around 250 microseconds to go from the low point to the high point. Let's remember this value. We will explain it later on. We can go and explore other regions and see what the differences are. So here, where we have a gradual climb, we also see that the enhanced waveform is shifted to the left. In the noisy region, again, we see that the waveform doesn't drop down as a step function, but instead it gradually climbs down, and it starts climbing down before the true waveform drops down. So in some sense, the whole waveform here is shifted to the left, because the drop starts even before it starts in the true waveform. Now that we understand how the enhanced waveform differs from the true one, let's go ahead and apply a low-pass filtering to channel B. Which filtering frequency should we use? And I will show you the formula that will link the bit resolution enhancement with the filtering frequency. To do that, we will notice that we went from 8 bits to 12 bits in our resolution enhancement. That is the difference of 4 bits. We need to take 2 and raise it to the power of 4, the 4 bits that we added, and we will get 16. Take 16 and square it to get 256. Now notice that we are sampling at 1 megasamples per second. So take 1 million and divide by 2 and divide by 256. You will get approximately 2000. So this is the frequency that we are going to enable in our low-pass filtering. So let's do just that. Activate low-pass filtering at 2 kHz. Let's see if we matched our waveforms. So let me move one of the waveforms a little bit up, and we'll see how closely they resemble each other. Let's reset the offset. Okay, it doesn't want to do that. That's too bad. Picoscope has some issues, not that many, but it does. Ouch. Oh well. Alright, here we go. So let's zoom on that region that is a step function in the original waveform, and what we see is very similar pictures. We have the blue line that goes straight up from one point to another, and the red line that is filtered at 2 kHz is almost the same, but it is smooth. So the filtering changes the step function into a smooth rise, and the bit resolution enhancement changes the step function into piecewise linear functions. Other than that, there is very little difference. We can check other regions and see that they are almost the same. In the region where we had noise, again, we see that they resemble each other, but when there is a sharp drop, one will be almost a straight line, another will be smooth. Returning back to the sharp transition here, let's explain why we observe 250 microseconds. To do that, we need to calculate the period of a 2 kHz frequency. So we need to take 1 divided by 2000 and get 0.0005, and then if we divide that number by 2, we are going to get 0.000250, and that is exactly your 250 microseconds that you are seeing here. So the whole transition takes half the period of a 2 kHz, or if you're using a different frequency, half the period of the frequency that you are using. To summarize, bit resolution enhancement and low-pass filtering are very similar in their results, but one of them tends to produce straight lines and another one tends to produce smooth curves. we know the formula that connects the two, and also we need to be aware that if the true waveform is a step function, then the transition will actually begin earlier, and the length of that transition will be half period of the filtering frequency. Note that in this example, we are using relatively low filtering frequencies compared to the sampling rate. If your filtering frequency is above 1/10 of the sampling rate, you might see different results. Also note that these results are applicable only to Picoscope. Other oscilloscopes might have similar features, but they might be implemented somewhat differently.